Alright, so today I'm going to go over the part of the notes where we're going to be talking about Dalton's law and how to apply that law. So here's what Dalton's law is. It says that if you know what the total pressure of the gas is in a mixture, it's equal to the sum of like the individual parts or the individual pressures of each gas that are in the mixture. So that means if you have a container and we have one big container of gas right here, and let's say we knew that the total pressure were 5 atmospheres of pressure, right? And let's say inside this container, you knew that it was made up of, I'm just going to name some gases. We'll say like one of the gases is oxygen gas, or one of the gases is nitrogen gas, and one of the gases is CO2. Okay. Let's say, I'm just making up some numbers. We'll say that the partial pressure of oxygen is like 1 atm. And then the partial pressure of nitrogen is 2 atm, then with that information, you should be able to figure out the partial pressure of carbon dioxide, because I know that the oxygen pressure, the nitrogen pressure, and the CO2 pressure, they're all going to add up to 5 atms like that. So this is 1 and 2, so that's 3. So I know that the partial pressure of the CO2 is going to be 2 atmospheres total. So that's pretty much what Dalton's law is in a nutshell, that the partial pressures of each gas that make up a mixture is always going to add up to the total pressure of whatever the gas is inside of the container right there. So our total pressure in that scenario was 5 atmospheres. Now, looking down below, we could look at the equations that we're going to be utilizing here. And remember that if you're looking at one container, you know that the R constant doesn't change. It's still 0.0821. The temperature is not going to change because it's the same container. And the volume, obviously, is not going to change at all for the gas itself. And this thing that you guys see right over here, the P total is equal to N1 plus N2 plus N3. Remember, the N stands for the number of moles of gas. And the 1, 2, 3 could just stand for the individual gases themselves. So like, for example, N1 could be the moles of oxygen gas, or the N2 could stand for the moles of nitrogen gas, or the N3 could stand for the moles of CO2 gas. And then we're just rewriting PV equals nRT. So you know PIV nert, we've learned this when we talked about the regular ideal gas law. And just to solve for pressure, I'm going to solve for pressure by taking nRT and then dividing it by the volume right there. So you could see that by dividing that out, I could get pressure all by itself. But the number of moles, the N right here, is made up by adding up the moles of all the different mixtures of gases that you have. So you could have like oxygen, nitrogen, and CO2, back to our regular example. So we're looking at a variation of PV nRT right here when we're looking at more than one type of gas. Now, in relation to Dalton's law, a more important concept for you guys to understand is something called the mole fraction right here. And the mole fraction is pretty much just what it sounds like. It's a fraction of moles, and it's a fraction with the moles of the substance divided by the total number of moles that we're actually looking at of the gas. So just in our example over here, let's say that we had, I don't know, like for the O2, let's say we had 1.5 moles of the gas in the container. For the nitrogen, let's say we had 2 moles. And then for the PCO2, let's say we had 3.5 moles. I'm just making it up, not based off the pressures over there. I'm just coming up with new values of moles right there. So if I wanted to know the mole fraction of, let's say, nitrogen, I'm going to take how many moles of nitrogen I have, so 2.0 moles of nitrogen, and I'm going to divide it by all of the moles added together. So 1.5 plus 2 plus 3.5, that's going to give us 7 moles on the bottom. And when you divide the 2 by 7, you're going to end up getting your mole fraction of I use 2 sig figs, so it's going to be 0.29 as our mole fraction right there. Okay, now an important way to understand this mole fraction, though, is that if you know what the mole fraction is, we just did this calculation over on the right side, the number of moles divided by the total number of moles, I could also set it into ratio with pressure. So on top is the pressure of the gas, And then on the bottom is a pressure total inside the entire container. So let's practice using this idea of mole fraction and relating it to Dalton's law down here below. So this time you guys are told that in air, you know that air is a mixture of different types of gases, but the partial pressure of nitrogen in air is 592 torr. So this is my pressure of just nitrogen. So PN2 is 592 torr. The total air pressure is 752 torr. So this is my total. It says, what is the mole fraction of nitrogen? So simple, I'm trying to solve for what this is, the N1 over N total, but I know the information here. I know that the P1 on top is 592 torr for the nitrogen. I know the P total is 752 torr. So if I just divide that number, I could figure out what the mole fraction is right here. So I'm going to just write mole fraction is equal to my P1, which is my pressure of just nitrogen, so 592 torr, and I'm going to divide it by my total pressure of 752 torr. Okay, so we're going to go through and just divide that out. And we need 3 sig figs, so I have 0.787 as my mole fraction. This means about like 79% of the air molecules we have, they're made up of nitrogen gas. So it's giving you an idea for how many moles there are of nitrogen relative to the total number of moles we have of gas. Now, let's look down below. Now it says, what is the partial pressure of nitrogen? So this time you guys are solving for PN2. They want the partial pressure of nitrogen if the container holding the air is compressed to 5.25 atm. Okay, so we know the P total, it's going to be 5.25 atm. And I'm looking for the partial pressure of nitrogen. So our basic setup is going to be N1 over N total. And earlier, you guys remember we solved for that right here. The N1 over N total is equal to 0.787, right? And I know that 0.787 is now equal to P1 over P total. So I don't know my partial pressure of nitrogen, so that goes on top. My P total is 5.25 atm. And I'm basically just going to cross multiply and solve for PN2. Okay, so I'm going to take 0.787 times it by 5.25. So I took my mole fraction of 0.787. I'm multiplying it by my total pressure of 5.25 atmospheres. And now I found out that my partial pressure of nitrogen, it's going to be a fraction of the 5.25 and 3 sig figs, so 4.13 atm for the partial pressure of nitrogen right there. Okay? Now, the second part to this problem, or not second part, but another way we could use a problem like this with Dalton's law is actually a little trickier. We have a system with 3 different containers, and they're all connected together with some tubes, and there's a valve that's connecting them here, and there's a valve that's connecting them right here. So the valve could be open and closed, but when they're open and closed, they present pretty different pressures of the gas. So in this first container, we have just methane gas. We have 4 liters of it. And we know the pressure in the container currently is 2.70 atm. And currently, guys, the valves are actually closed. In the second container, it's a 1.5 liter container of nitrogen gas. I know the pressure there. And then in the third container, it's 3.5 liters of oxygen, and I know the pressure right here. Okay? So now the problem is saying when the valves are actually opened up, so these guys are going to get opened up right here. All right, so we're going to open up those valves. What is the partial pressure of each gas, and then the total pressure altogether? So one mistake that people make is when they see that the question is asking for total pressure right here, they just go, oh, easy, I'm just going to take the pressure here, the pressure here, and the pressure here, and we're going to add it all up to get the total pressure. But the reason you cannot do that over here is that these containers are different sizes. Like this is only 4 liters, that's 1.5, that's 3.5. But when the valves are actually opened, the volume changes. It's no longer 4 and 1.5 and 3.5. We're going to add it up. So it's 4 plus 1.5 plus 3.5, and you end up with a total amount or the volume for all three containers is 9 liters. And essentially to do this problem, what you're going to be doing is you're going to be doing a P1 V1 is equal to P2 V2 setup. And we're going to be doing that for all of the gases here. So P1 V1, P2 V2. And pressure 1, volume 1 is the initial condition before we open the valves. P2 V2 is a condition after we open the valves over here. So I'm going to do the first one with you guys. The second and third I'm going to have you guys do on your own. For the P1 inside this container, you know it's 2.70 atm. The volume of this container is 4 liters. Now the pressure too, I want to know what the pressure is of the gas once we change the volume, so I don't know it. The volume too is going to be the total volume for everything, so this is going to be 9 liters. Okay, so we're going to go through and just multiply and divide. I'm going to do 2.7 times 4, and then divide that by 9 to get my P2. So my new P2, I'm going to just solve it down here. My new P2 ends up as 1.2 atm of pressure. So this should make sense. My gas container went from 4 liters to 9 liters. So the pressure also dropped. Instead of 2.7, now I'm at a 1.2 atm of pressure for just the methane gas. And let me show you guys what the setup is. I'm just going to punch in all the numbers and then I'll show you what it's going to look like. So you could see here I set up the second equation using the exact same method that we talked about before. And then the third equation, I'm doing the exact same thing as well. And we're going to go ahead and solve for P2 for each of these down below. So I'm going to just do the same thing I did before, 4.58 times 1.5, divide that by 9. And then for the P2, I got 0.763 atm. Again, the pressure dropped from 4.58. Same thing over here, 0.752 times 3.5 divided by 9. And then for the P2 here, we're going to end up with 0.294 or 292 atm. Okay, and again, one more time, notice how all the pressures dropped upon opening up the valves. You went from 2.7 to 1.2, 4.58 to 0.763, 0.752 to 0.292, and then these three pressures to get our final answer to the question, they wanted us to solve for the total pressure once all the valves were open. We're going to take all the individual pressures, 1.2 plus 0.763 plus 0.292 atmospheres, and we're going to get our total pressure out of this that way. And I got 2.255 atm of pressure. We're adding these, so you have to go to the smallest number of decimal places. So I need 1 decimal place. So it's going to be 2.3 atm for P total right here. And that is it.